Yes, that is live to the Zoom.
Chris and Rick, just a quick note for you both, if you can hear me.
Yep.
Great. So the order of operations, and I don't see Chris. So once Chris gets back, I will just give you a quick update. You see, Magnus is here.
Okay.
All right, I'll be back on in a minute.
One second. This is a stream test, testing the stream. You are hearing audio now from me, testing into the stream. Hopefully you will hear my voice. We have taken music out. Yeah, so Tony's hearing it in the room, but yeah, I do want to make sure that it encodes properly out to Nathan. So I'm just going to keep talking for a little bit and just keep vamping until we get full confirmation that we are good and cleared and that everything is going good. So I'm really good at this, Tona. I can vamp for a really long time and just keep... Excellent. Thank you very much.
Hello? Can you hear me? Just nod.
Yep.
Great. Okay, so a slight modification to the order of operations. Magnus is going to, Kevin, our current president, is going to welcome attendees, share housekeeping notes. Magnus will then come to the stage, introduce both of you, present the awards to you first before your presentations. That's the big change.
All right.
And then, Chris, you're presenting first, correct?
No.
No.
It's Rick.
Rick is presenting first. Questions. Chris presents. Questions. Questions for both of you. And then the session will end.
Sounds good.
So the major change is that you presented your awards before, Rick, you give your talk first.
And the other thing then is it ends at 3:15.
Correct.
So that's helpful for me to know.
Great. All right. We will get started here in about 5 or so minutes. I'll just give you the thumbs up when we're going to get started. All right. Thank you both. All right.
Good afternoon, everyone. Yep, that was just good afternoon, everyone. Hope everyone's having a great time. Yeah. So, the games, so if, go ahead and you fill out these, bring the cards. There's numbers on the bingo sheet. And if you go to the, in the exhibit hall, so, and even if you don't play bingo, please come to visit our corporate partners. They're anxious to talk with you and interact. But before we get started with the meeting, a little housekeeping. Please silence your phones. Photography and video recording of the sessions, as before, are prohibited. ABRF social media policy that everything can be shared, but if a speaker asks that you don't share it, please honor that request. The hashtag for our event is hashtag ABRF 2023. Recordings of the program will be available on the meeting site website in a few days. Remote participants may post lines on the online chat, but if you're going to ask questions in the room, please come up to the microphones. With that said, I'd like to introduce Magnus Palmblad, who will be introducing our ABRF awardees.
So the ABRF award is given annually to a scientist or scientists who have made outstanding contributions to biomolecular technologies, recognizing pioneering achievements and developments of powerful new tools that underpin the biological research enterprise. The 2022 ABRF award, which is awarded this year at the meeting, is given equally to Professor Emeritus Christy Enke of the University of New Mexico and Professor Emeritus Richard Yost at University of Florida, in recognition of the development of the triple quadrupole mass spectrometer and the tremendous impact triple quadrupoles have had for a wide range of biomedical research applications. Their accomplishments are far too many to list in full here. You can look on Wikipedia or online. You have lots of information about the awardees. The ABRF is also not the first to recognize these particular achievements. The recipients shared the ASMS Award for Distinguished Contribution to Mass Spectrometry in 1993, with Chris Enke also receiving the American Chemical Society's Award for Analytical Chemistry in 2011, and Rick Yost, the MSACL, the Mass Spectrometry in Analytical and Clinical Laboratories Award in 2018, all for their work on triple quadrupoles. The ABRF Award further recognizes this pioneering development of a technology that is now ubiquitously used in mass spectrometry core facilities and an essential tool for practically every clinical and environmental chemistry laboratory in the world. It's therefore a great honor for me to virtually present the award to Professors Chris Enke and Rick Yost. So I will virtually transfer the award. And with that, I think Rick Yost will go first. So we look forward to looking and hearing your award presentation. Take it away.
All right. Thank you, Magnus, and thanks to all of you who are there in the room. Chris and I wish we could be with you. I'll briefly throw the award up behind me there as if I were holding it up in front of you all. And then I'll go back to the other background. But this is a great opportunity to celebrate development of new tools that drive the biomedical research enterprise, and that's what we're talking about today. So let me share my slides. So hopefully you all can see up on the screen my first slide. And so I want to tell you today about the role of tandem mass spectrometry, or tandem methods, or hyphenated methods, if you like that term, for mixture analysis, particularly trace mixture analysis. And so let's first go back and think a bit about what Magnus read when he was talking about the award. He says, the award text says, technology is a driving force behind scientific advancements. And I think we'll all embrace that as members of ABRF. You are very, used to using these new technologies to drive science forward. Also discusses powerful new tools that form the foundations upon which the modern biomolecular research enterprise thrives. And I think this is a wonderful opportunity to celebrate those tools. And as you think about, all the advances in science, they tend to be driven by tools and technologies that let us either measure something or see something. That could be, litmus paper or telescopes on the top of mountainsides or mass spectrometers. So Chris and I are very honored to receive this award today, and we very much appreciate all that ABRF does to celebrate new tools and the development of new tools. Okay, so if we go back 45 years, and it's been a great opportunity for Chris and I to do that as we've gotten ready for these talks. It's kind of fun to think back to the development of the triple quad. This is an analytical chemistry A-page article, as we used to call them, at about that time, talking about triple quadrupole mass spectrometers, image from the very first grant proposal we wrote to build that instrument, and Chris and I there. If you would like to hear more about the development of the triple quad, because Chris and I won't talk about that today, you might want to go back and watch this YouTube video. You can copy that down, but if you simply Google YouTube, Yost and Enke, you'll find it. And this was a chance for Chris and I a few years ago to reminisce about that development. And there we are standing in front of that first instrument. I would point out that Chris and I haven't changed a bit in 45 years. So what are our topics today? Our talks together are entitled Mixture Analysis Strategies and Future Directions. And part one that I will present is this role of tandem or hyphenated methods for trace mixture analysis. So I'm going to talk about principles of tandem analytical techniques, such as GCM-SMS or LCM-SMS. I'm going to talk about the capabilities and requirements for such tandem techniques, things you have to think about. I'll talk a bit about the role of sensitivity and selectivity for trace analysis. Then I'll talk a bit about added resolution elements for challenging problems, and I'll pick one to talk about today. I'll talk a bit about ion mobility separations. And then I'll try and give you some examples of trace analysis using these tandem techniques. And then part two, Chris is going to talk second, and he's going to talk about untargeted analysis, a simple check on how much we're missing, and provide an invitation to you all to engage in that. So that's our roadmap for today. So let's see. Let's talk first about the capabilities and requirements of these tandem techniques. First, let's think about capabilities. One is that you have more confidence in your analytical results if you have more than one handle on your analyte, be that retention time and mass, or pick your favorite tandem method. Secondly, we have the ability to handle more complicated samples, more complex samples than we could by a single non-tandem method. Third capability is improved detection limits. We generally see lower detection limits when we use these tandem methods. That's why they're so important in trace analysis today. They also involve minimization of method development. And some people would argue with me about that, but I would say that if you're developing a chromatographic method, for instance, for a single analyte, or for an analyte in a mixture, that one technique, say liquid chromatography, has got to separate everything else from it, and that can take an awful lot of method development. If, on the other hand, you have a tandem method, say LC mass spec, you don't have to worry about that. You can rely upon the second technique helping to solve your problems. What are then the requirements for such a tandem analytical technique? First is the instruments are more complex. An LC mass spec is more complicated than LC with a UV detector. Secondly, it generally requires increased user sophistication, although mass spectrometers have gotten much better in the last decade or two at not requiring quite as much knowledge on the part of the person sitting in front of them. But you all, I think, will agree that such instruments require, better trained and more sophisticated users. And finally, the ability to handle enormous amounts of data, three-dimensional data like this, obviously higher dimensionality. When Chris and I started this, that was a big issue. These days, it's not nearly the issue it once was because computing power has gotten so much better. All right, let's consider an example. Let's consider analysis by GC or LC, whatever you prefer, compared to GCMS or LCMS. So if we're doing just one stage of chromatography, GC or LC, this is the data we have. Intensity versus retention time. It was just a chromatogram, of course. But when we add that a second stage, a tandem method such as mass spectrometry to that, we now have the whole chromatogram, but at every point in time, we have a mass spectrum as well. And so let's think then about how we would use that in an application, and you can pick your favorite. That could be pesticides in food. It could be measuring trace levels of drug in an athlete. Pick your favorite kind of analytical scheme. But whether that's GC or LC combined with mass spec, let's think about it. So monitoring both retention time and mass obviously increases the confidence that we know that when we see that peak, we're indeed detecting the analyte we're looking for. Secondly, we can handle more complex samples because we aren't relying upon one stage, say chromatography, to do it all by itself. Furthermore, typically you get lower detection limits by things like GC mass spec or LCMS than by GC or LC alone. And it minimizes method development because now chromatography doesn't have to do all the heavy lifting itself, assuming that two overlapping peaks don't have the same masses, we can resolve them by mass spec instead of relying upon chromatography. That said, we will all agree that a GCMS or LCMS is more complex, requires more user sophistication, and produces a lot of data. Okay, so one of the first people to talk about this kind of concept of tandem, or as he called them, hyphenated methods, was Thomas Hirschfeld 40 years ago. And Thomas, in another analytical chemistry article, had this wonderful chart that talks about all the different combinations he could think of at the time of different analytical techniques combined with other analytical techniques. The ones with black dots were possible, he thought, at the state of the art. The ones with orange dots, ones that have been demonstrated so far successfully. But if you look, the ones that he really highlighted, and the ones that we'll highlight today, are GC and LC combined with mass spec, or even mass spec combined with mass spec. Looking back again, an early person who talked about these concepts was Fred McLafferty. He talked about the 4 S's of trace analysis. So let me remind you what he had to say. He said that the first S for trace analysis was sensitivity. That is, of course, the change in instrument response for a change in analyte concentration or amount. Obviously, an important figure of merit for an analytical method. He said equally important was selectivity, the second S, freedom from interferences, freedom from other things that we might detect and think are analyte when indeed they're not our analyte. And indeed, at that time, the term chemical noise was coined to describe those interferences. The third S, he said, was speed, analysis time, including sample preparation and separation, obviously an important figure of merit. And the fourth S, he said, was the almighty $sign, the total cost of analysis. So we can argue about these last two, and they are oftentimes very important in practical analytical schemes. But let's just focus on the first two if we can. Some definitions. So sensitivity, as we think of that figure of merit, is simply the slope of a calibration curve. If you think of it in a mathematical expression, it's d signal over d amount. So if we want to get a reasonable signal on the top for a very small amount of analyte on the bottom of this fraction, then we need high sensitivity. That ratio has to be high. I think we all recognize that. But equally important when analyzing not standards, but real samples, is selectivity, a business of being sure that the signal we detect is due to our analyte and not due to something else. And selectivity is generally hard to define mathematically, unless you're in very simple cases. If you're talking about an ion selective electrode for sodium and what is its selectivity versus potassium, that's easy. In cases like LC mass spec, it's much more difficult to come up with a general expression for selectivity. But most of us, when we think of selectivity, think about it in terms of its impact on limit of detection. Limit of detection, of course, is the lowest amount of analyte that you can detect in the presence in a real sample. UPAC would say that's the amount or the concentration, which gives us a signal to noise ratio of 3. Or if you combine those equations, then the limit of detection is 3 times the ratio of noise over sensitivity. So for many analytical instruments, noise is dominated by instrumental noise or electronic noise. Not the case in mass spectrometry. Our instruments are so good that the noise that limits us is chemical noise interferences. Even if you put no sample in your mass spectrometer, you oftentimes still see signals at various masses. So let's think about that. To get low limits of detection, where we want to be, we need high sensitivity. That's on the bottom. That makes perfect sense. But we need low noise. And how can we reduce chemical noise? And that's the key of selectivity. Okay, so how can we improve our selectivity? Going back one more time to the early days, Graham Cooks talked about improving the selectivity by combining in tandem complementary techniques, or what he called more stages of analysis. So this paper in JChem Ed, all the way back in 1982, 40 years ago, showed this graph, and let's kind of talk about that for a moment. On the x-axis is numbers of stages of analysis. So for instance, one stage might be LC or GC or mass spec by itself. 2 stages might be LCMS, 3 might be LCMS-MS. And if we want even more, what if we added another stage, say ion mobility, and did LC ion mobility mass spec. So let's look at what the curves tell us. The first thing you see if you look at the signal is that as you added more stages of analysis, the signal goes down. Okay, so that might be interesting or maybe even startling to some people, but think about, for instance, MS-MS. If you add a second stage of mass spectrometry, you won't have 100% transmission through this added mass analyzer, no 100% conversion of parent ion or precursor ion to product or fragment ion. So the signal will go down. So listen carefully, tandem methods are inherently less sensitive. The signal goes down. So why would you do them? The reason, of course, why we do tandem methods is to reduce chemical noise, to be more selective. And if the chemical noise goes down even faster than the signal, our signal to noise ratio goes up, and therefore our detection makes it better. And that works as long as chemical noise dominates over instrumental noise. And in mass spectrometry, that's almost always true. Instrumental noise is typically very modest. And therefore, more stages of analysis reduce the chemical noise, reduce the signal too, but inevitably improve signal to noise ratio, give us better detection than that. So let's think about a couple of examples of tandem analytical methods and see if that makes sense to us in terms of selectivity. First, let's think about optical methods. Think about absorption spectroscopy, where we have a light source, pick one wavelength with a monochromator, pass that into our sample in a cuvette, and look at the amount of light left over at our detector, how much is not absorbed. Now let's think about, in that sample cuvette, what would be necessary for another compound to interfere with the detection of our analyte, the thing we want to detect? Well, it would have to absorb at the same wavelength as we picked with that monochromator, the same wavelength as our analyte. Okay. But what if we go to a 2-stage method like fluorescence spectroscopy with 2 monochromators? Now, in order for a compound in that sample cuvette to interfere with our analyte, it would have to not only absorb at the same wavelength as we picked for the first monochromator, the same wavelength as our analyte, but it would also have to fluoresce, and would have to fluoresce at the same wavelength as well. So inherently, 2 stages of analysis in fluorescence spectroscopy: less signal, less photons reaching the detector, but more selective, therefore lower limits of detection. We can use the same model to think about mass spectrometry. Think about MS, for instance. There's a sample put in the ion source, 1 mass analyzer detector. For some other compound to interfere with our analyte, it has to produce the same mass, or masses if you're looking at more than 1 mass, in the ion source as our analyte. So that would be what would be a problem and cause interference. But in MS-MS, where we have now 2 mass analyzers and a collision cell in between, now for that compound to interfere with our analyte, it not only must ionize to make the same mass, but it must then dissociate to form the same fragment mass as well. More selective, less signal, but more selective, lower limits of detection. And of course, that's the reason why we use tandem mass spectrometry in mixture analysis. Okay, so that kind of opens up the question of why not just make this first stage really, really good? Why don't we just increase the resolution of one single analytical stage instead of using tandem methods? Let's think about that in terms of the way most of my colleagues do. They say, well, I just want to do great chromatography, then I won't need that mass spectrometer there. So let's think about that question. Why not just do great chromatography? So let's pick a natural product, peppermint oil, run it on a pack, carbowax column, a 2-meter pack GC column. Yeah, there's a dozen compounds. There may be a few more because there's some things obviously aren't resolved. But if you take that same sample and put it on a 50-meter capillary column, you find, oh, there's way more than that many compounds there. Then we open up the question, well, now what if I went to 100 meters or 500-meter capillary column? How many more compounds would I see? Well, great chromatography just saved me by itself. We can model such separations, and it's actually been done for us. Giashone and Giddings independently, back in the 80s, came up with a model for component overlap in capillary GC. Works just as well with HPLC or CZE, pick your favorite analytical separation technique. And these were the definitions they used. They said N is peak capacity. That's the maximum number of resolvable peaks if peaks came out of the chromatographic column, one right after the other, just resolved from the one in front of it. Maximum number of compounds you could separate if they were perfectly, lined up in order. And then M, they said, was the number of components in your mixture. And therefore, they defined a saturation factor M over N, the number of mixture components versus the number that you could theoretically separate at it the best. And thinking about a capillary GC column, for instance, a 30-meter cap column at 3,000 plates per meter, kind of a typical value, yields a number of peak capacity N. That's about half the square root of the number of theoretical plates. So it's about 150 peaks in a 30-meter column running over 30 minutes. All right, so that gives us an idea for peak capacity. So let's see, what if we had that column? We said N was 150, we could ideally separate as many as 150 components. And we use a saturation factor of a half. We put a 75 component mixture onto that column. What happens? So Gidding and Giashone's model came up with the same results, assuming that the peaks elute at random times, and that everything has equal concentrations. Now, those are not real cases, right? Homologous series oftentimes elute not randomly, but in order. And oftentimes we care about a little peak in a chromatogram, so equal concentrations is not as challenging as the real situation. But their models both predict 75 components. That mixture will produce a chromatogram with just 45 peaks, not 75 peaks. About a third of the components would come out as single component resolved peaks. There'd be quite a few peaks that have 2 components hiding beneath them, some with 3 and some with 4 or more in this model. So in the end, 45 GC peaks from a 75 component mixture. Clearly, we need something to help resolve the things that are not resolved by chromatography. So let's think about a real complex mixture. Let's say that we want to separate 90% of all the components as single component peaks. That would be our goal. And it's not 100, it's just 90. That requires a saturation factor less than 0.05, they said. So let's pick a real number. Let's say I have a 100 component mixture, and I want to separate 90 of those as pure peaks. The other 10 can overlap. I'm okay with that. That would require a capillary GC column with 20 million theoretical plates. But 3,000 plates per meter, that's a column that's 6.7 kilometers long, 4 miles long. And even if you can make such a column and you were patient enough, the retention time is going to be a week, and peak width will be an hour for each peak. So the peaks are going to be undetectably low. So this is not practical to even separate 90 components out of a 100 component mixture by chromatography by itself is not a practical exercise, is what they told us. The solution, of course, is tandem methods, things like GCMS or even GCMSMS. So let me give you just one example of GCMS versus GCMSMS for a particular example, particular analyte. This is methotriptyline related to alcoholism. It was postulated looking in rat brain. This is work we published back in '84. And this is the GCMS trace looking for methotriptyline. And see, what have we done? We've first derivatized this mixture with heptafluorobutyric acid in order to be able to, A, get everything to the GC column, and B, since we're derivatizing anyway, to put a bunch of fluorines on there to make it really sensitive and electron capture negative CI. So negative CI, we're monitoring a negative ion. To maximize our sensitivity, we're going to do selected ion monitoring just the 362 minus ion for methyl-tryptamine here. There's no discernible GC peak for methyl-tryptamine. There's the retention time of the standard. It's not there. That's problematic. But what if we then add another stage of analysis and say, what if we do GC-MS-MS? So here's that trace now. And what do we see? Indeed, there's a great peak for methyl-tryptamine right there, monitoring the 179 minus fragment ion of 362 minus. There's only one other peak in the whole chromatogram. Everything else, all the rest of this stuff up here is gone because it doesn't fragment to form 179. Perhaps the most dramatic example of how much an improvement MSM has provided in this case is, let's look at the baseline up here at the top. Pick the lowest point in that chromatogram and look at this baseline. Call that the baseline. The baseline down below in MSMS is 3,000 times lower. So not every example will MSMS give you that kind of selectivity, but it is a pretty remarkable example of going to now, in this case, 3 stages. GC-MS-MS solves the problem for trace analysis. And most of you in the audience can come up with your own examples, so they'll be similar to this. Okay, so I want to leave you with one last kind of question about if 3 stages is good as 4 better. Can we use other stages of analysis? And the one I want to talk about is ion mobility, not in GC-MS, but in LC-MS. So let me tell you the example I'm going to talk about. I'm going to talk about detecting or measuring 25-hydroxy D3, vitamin D3, in plasma. One of the most common clinical assays in the world today. Many people are vitamin D deficient, or at least think they are. And 25-hydroxy vitamin D3, here's the molecule. There is an epimer of it, 25-hydroxy epimer D3. Same elemental composition, same structure, except for one of the chiral carbons, just this one chiral carbon, the chirality is reversed. So the epimer is an interferent in this case, as isomers oftentimes are. And we can't separate it easily by chromatography, perhaps not at all in any reasonable chromatographic separation. We can't separate it by mass spectrometry. Would ion mobility be able to help us? Now, let me point out that we're going to do this by LC with electrospray mass spec, and this compound is not protonate under electrospray conditions. It's not basic enough to pick up a proton, so we wouldn't see it. But there's enough sodium around in our columns and our solvents and plasma extracts that we form a nice M plus sodium ion. So we don't have to worry about that. We're going to look at the sodium adduct of this. Okay, so if we now look at, with an ion mobility spectrometer on a quadrupole time of flight instrument, look at the drift time of that. 25-hydroxy D3, the green compound, the one we care about, gives us 2 drift peaks, interestingly enough, whereas the epimer, our interferent, only gives us 1 peak. And the separation up here is really not good enough to be able to detect 25-hydroxy D3 without an interference from the epimer. But the second peak looks very promising. There's no epimer peak out there at all, and 25-hydroxy D3 shows up all by itself. So what's happening here? And when we go look at this and do some electromodeling, we find out that the lowest energy conformation when sodiated is for the 25-hydroxy D3 is that one sodium associates with both hydroxyl groups and gives us a closed conformation, which of course is going to be smaller than an open conformation. We also see the open conformation. We know which end the sodium sits at for the lowest energy. And so we do see that peak. That open conformation we can calculate is about 2 kcals per mole less favorable. And under electrospray conditions, we populate both of those. So we see both a closed and an open peak, an early and a later peak. The epimer, on the other hand, remember, doesn't give us a second peak. You get the same closed conformation, and there it is. The open conformation, if you do the calculation, is 8 kcals per mole less favored, and under electrospray conditions, it just never shows up. So this is a great example where the ion mobility gives us a little separation for the closed conformation, but completely resolves the open conformation. So the obvious question is, based on this open conformation, the second mobility peak for 25-hydroxy D3, can we quantitate based upon that? And the answer is yes. There's a calibration curve, so in calibrators, plasma QC samples, and so on, over the reasonable clinical range. R squared, as for many calibration curves, is embarrassingly good. Standard deviations, 1 to 5% RSD. Limit detection about 5 nanograms per mil. That's certainly low enough to handle even low vitamin D deficient individuals. This currently still uses a 2-minute HPLC separation, which is quite reasonable for a clinical assay, but we're working on taking that down to 10 seconds, obviously with no liquid chromatography. I mean, I think about other ways to build some selectivity and besides LC. All right, so in conclusion of this first talk of these two, I think you all agree with me that advances in science are driven by the development of new tools, including tandem analytical methods, things like GCMS, LCMS, and tandem aspect. Understanding the principles of such tandem methods, as I've tried to share with you today, I think has helped lead to powerful new tools and better ways to use those tools by understanding them, I think. I'm confident that that will continue to go on, that we're not there yet. So thanks for helping celebrate tandem aspect, tandem methods in general, and indeed celebrating all those tools and methods that enable us to advance biomolecular science. So thank you so much. We can take some questions now on my part if there are some, and then we'll go on to Chris's part for part 2. So thank you all.
There's no questions. We'll move on to part 2.
Let's go. We save the best for last. Let me stop sharing because Chris is going to want to share his slides. There we go.
Is my speaker on?
Yes.
Okay, so thank you, Rick, for your great talk. What I want to talk about today is on the degree to which our untargeted analysis are actually comprehensive. Are we really getting enough of the compounds that are in the sample, and what might help us to see more? I want to start by giving my thanks to ABRF for considering Rick and me for this prestigious award. The triple quad, and indeed the process that enabled all MSMS instruments, started with Rick choosing my vision of a computerized analytical instrument for his thesis project. I needed separation and identification stages that could be computer controlled, and Rick suggested the quadrupole mass filter to perform those tasks. The problem was, we were told there was no way to efficiently fragment the ions between quadrupole mass analyzers. The only way that was known at that time required several thousand volts of acceleration for the ions, and that, of course, is incompatible with the voltages used in quad instruments. But then, serendipitously, we heard Jim Morrison's frustration over all the background fragments he was getting while he was trying to study photodissociation. Now, the key was his quadrupole fragment containment chamber that he had between his selector and his analyzer. So Rick went to Morrison's lab to see what was creating those fragments. And low energy collisional fragmentation was employed in our instrument design, and that was the beginning of all the currently used MSMS instruments. And you can hear the whole story of that if you go to my Wikipedia page and check and click on the video. The work I'm talking about today, the nature of complex mixtures, owes much to others, beginning with Luke Nagels, whom I worked with to discover how the responses to the compounds in natural complex mixtures are distributed. Data contributed by other labs confirmed our hypothesis, and a collaboration with Alex Gundlach-Graham showed the role liquid chromatography plays in mixture analysis and how the distributions of concentrations and response factors are related. You've seen this picture before. Tandem mass spectrometry with high-resolution mass analysis has enabled analytical methodologies we couldn't even have imagined just a decade or two ago. And we're still making it better. As Rick has pointed out, the tremendous gain in selectivity. In Rick and my original instrument, we had about 1% transmission efficiency from the initial mass filter into the collision chamber, and another 1% transmission efficiency from the collision chamber into the quad. So we were seeing like 1/10,000th of the ions that we started with. And still, it was more analytically powerful for the very reasons that Rick has mentioned. So the key here is the ability to distinguish more compounds in the sample mixture through increased selectivity, as Rick has so ably told us about. And of course, the advent of computer control and computer analysis has made the possibility of dealing with that much information possible. Now, I'm hopeful that a number of you are involved in untargeted analysis in your lab. And I'm hoping to engage you in something we'd like to learn more about complex mixtures. As dramatic as the number of components we're detecting already, it is undeniably just a fraction of those that are actually there. And how big is that fraction? So if we wanted to detect more of them, well, how many more are there? What actually are we missing? And what would their responses be? What would it take to get there? Now, what we're really asking is a question which is difficult to answer if you can't detect it. In other words, we're really asking how can you see something? How can you quantify something you can't see? Well, you could only do that if we have a model, some expected function that those responses would contain. Then we could plot to see what that distribution would be. We need the response distributions, in other words, to follow a pattern. And then, of course, it would be nice to know what that pattern is. And if we know what that pattern is, then we can figure all that out. Well, there is a pattern. And it's been around since 1968 or earlier. I remember Sid Sigia giving a talk at Michigan State telling us about the logarithmic or the exponential function. And many, many people have repeated this over the years. And I'm wondering if you sort of have that expectation as well, or have heard that or accept it. Interestingly, the principal reference for this exponential model is this paper by Nagels in 1983. Uh, his was the first attempt actually to empirically verify Sidsidia's statement of the exponential model. And here are the data. Here's the plot that's in Nagel's paper. Dramatic increase in the number of compounds as the peak area, even this was done with chromatography, decreases. And it sure looks exponential. But if you actually read his paper, his paper says a significant lack of fit could be shown while trying to describe these experimental data with an exponential or gamma distribution. And the dots there are plotted against Nagel's data. The dots are the best exponential fit that could be made. And you see that it's really not doing very well at all. So I emailed Nagels and we got into a collaboration, which we carried on long distance. And it was very interesting to be able to do that. And we discovered that the function called log normal actually fit his data really quite nicely. Now, this log normal curve does increase steeply up to a point, but then it drops back down to 0. Now, if we take a histogram of instead of the peak areas, we histogram the logs of the peak areas. The result is, in fact, a familiar Gaussian curve. And in fact, that's what log normal actually means. It's normal curve if you make the histogram of the logs of the amplitudes instead of the direct values. So this is what we're saying, and this is really important here to understand. A log normal distribution is not some weird thing. It is a regular, normal Gaussian distribution when you make the histogram using the logs of the values instead of the values themselves. Now, if you plot it on a linear axis, it looks almost exponential, but in fact, at the high end, but at the low end, it's dramatically different. And because it's asymmetric, the mode, the median, and the mean are all different from each other. Now, you might ask, oh, what would produce such a thing? And why is this actually and I've seen several papers recently saying this is way more normal in life than we ordinarily think might be the case. And what you actually see is, when you think about a normal Gaussian curve, is sort of an equal distribution of additive differences, plus or minus the mean value. What the log normal curve is a distribution of multiplicative differences, greater or less, greater than 1 or less than 1, around the mean. So anything that would be multiplicative, for example, if you have a normal distribution of rate constants for a chemical reaction, the distribution of the products would be log norm. The distribution of the reaction rates, normal, but reaction rate times concentration gives you amount, and therefore the distribution of the amount would be log norm. And it's something that should be considered much more often than we are currently doing. Now here we have Al Marshall's lab, responses of light crude. And here we see the log plot, which gives you the normal distribution of the logs of Al's responses. And you see a very, very nice fit for this as far as they were able to take it. Now, of course, we get down to a response where we're below the detection limit and we can't see anymore. But now maybe we've got a model that tells us what we're missing. Now, here's something that I did not know before. And this is really interesting. If you now make this a log plot, in other words, you plot the log of the frequency against the histogram of log responses, you get a parabola. I did not know that a Gaussian curve was a parabola if you plotted the log of the frequencies. But it's really a lovely thing because you can fit this parabola in Excel, in half a minute, and you get out the exact parameters of that fit. And I've derived an equation that relates the A, B, and C parameters of the quadratic equation to the mean and to the characteristics of the log normal distribution. So let's look at that again. Here's the log. Here's the plot: log response versus frequency, log response versus log frequency. Now, here's where we are. And I invite you to try it. You can take your data and put it over in this column. It doesn't have to be in any order. And all this is just the amplitudes of your responses. This list can be 1 million responses long. This is an Excel spreadsheet. Okay, and then when you click this button, it will sort it and take the log. And then, I'm sorry, it'll sort it all out so that these are now in order. Then it'll take the log with clicking this button. And then from the logs of the data, you can decide what you want your interval for the histogram to be. You set that increment, you set the number of increments you want, and then you click this button that creates a table, and this button to get the frequencies. And when you've done that, you will get a plot. And this plot is an ideal data set. So you can see what would happen if you had a perfect analysis. This is the log frequency plot. So it's a parabola. This is the linear frequency plot. So it's a Gaussian distribution. And it will tell you then, of course, it'll analyze and give you the characteristics of the distribution that you got. Now, when you do this with your data, and I'm hoping that you will be interested in doing that, your curves will look more like this. Now, this is from the Yates lab. peptide in a yeast digest, and you see was able to do really quite well, and in fact got quite a lot down in here. But this is presumably maybe what we're missing is this area in here. He detected 80,000 peptides, and if the log normal distribution is in fact followed over here on the low side of the curve, then we're thinking maybe there's 100,000. So he's only missing 20,000, and that's really quite nice. But the other thing that we need to think about here for a second is that what we're looking at here are responses. They're not concentrations, they're responses. And the response is different from the concentration because of the response factor. And of course, not all the compounds have the same response factor. But this raises a very interesting question. If you think that there may be some natural reason why there should be a distribution of concentrations in a complex natural mixture, which is really interesting. I mean, Graham Cook says, why should there be a distribution? They're just things, but they must be related in some way. Otherwise, we wouldn't be getting these good fits. But not only then is the concentration, is the response logarithmic, I mean, a fit a model, but because the response is the concentration times the response factor, both of these must fit some function. Otherwise, the product of them would not be able to have a function itself. So if we assume it's the concentration that's log normal, what possible shape could the response factors have? And here's where Alex did some great work. He tested the distributions, assuming that the response factor distribution was any of these 6 distributions. Now, these are the response factors that he tested: Gaussian, beta parabolic, random, and log normal. This is what they look like plotted linearly. This is what they look like on the log plot. Okay, so which one of these do you think it could be? Well, when he then modeled all of these with a hypothetical set of data, what he came up with was that the log normal, beta high, and Gaussian distributions all followed the log normal parabola very nicely. That's this one, the log normal, and the black curve is what we started with, the concentration value. And then the rest of these are the response values. So the beta high and the log normal here look very close to, and the Gaussian look very close to the Gaussians over here, and I can't see it's behind something. So, so those are the things that would give us log normal on the low side as well. But interestingly enough, the other distributions that we checked gave actually more compounds on the low side than the log normal curve would provide. So they have positive deviations from log normal, suggesting that if they were the distribution of response factors, we're missing even more than we might have predicted with log normal alone. So how can we figure all this out? How can we decide which of these it is and how much we're really missing? Well, obviously, we can't do that unless we have more data examples that give us information left of the peak into the low concentration side of the peak. Now, for high resolution analyzers, so we need more dynamic range. And high resolution analyzers can't process enough ions at once to produce that wide a dynamic range. So for untargeted analysis, we would get maybe 3 orders of magnitude or less, dominated by the most abundant compounds. So we need to use some method to separate the sample into pieces, into bits. Not just diluting it. I'm talking about selecting it into so that the components of the sample are in different fractions of your set. And that's what we usually do. That's what Rick was talking about, exactly. The greater number of batches we can separate the compounds into, the greater will be our dynamic range. Because we'll be putting fewer compounds into our analyzer that can only take a certain number of ions, and that means that the least abundant compounds will have a much better chance of showing up. Now, extraction, chromatography, MS and MSMS are the most common means of creating these fractions. Chromatography, of course, has the advantage of being able to separate most isomers, except the one that Rick was talking about. But it has a complication that it produces fragments with various portions of various overlapping peaks and fractions of peaks in each segment. But and mass doesn't do that. Mass separation doesn't do that, but it also doesn't separate isomers. So we have maybe some combination of techniques that we use, but the main point that I'm trying to make is here, the more parts we can divide the sample up into, the wider our dynamic range is going to be. So here's what we know so far about the distribution of responses. It's log normal on the high side. It has been for every sample that we looked at, for every bit of information that we've gotten so far. This is for natural mixtures. It'd be very interesting to find natural mixtures that don't have that. I'd love to know what doesn't work. On the low side, the distribution of responses is going to depend on whatever the distribution of response factors is. We don't know that yet. But it could be log normal, or it could be some positive deviation from log normal. I mean, just finding out what a distribution of response factors would be really very, very much fun, I think, and very informative to what our analysis can do. So we can't totally predict the completeness of our analysis without knowing more about the response factor distribution. But here's what we could find out. Here's what would help if we could find this out. We could calculate the fraction of compounds, not only detect that that we're missing, and we can really imagine better what we need to do to improve the dynamic range that we've got, and therefore more a larger fraction of our compounds. Can we increase the ion throughput? Could we put more ions into the analyzer at once? That would help a lot. Can we adjust the fraction parameters? If we adjustment of fraction parameters, if we could move the most of, the top 3 or 4 compounds in a complex mixture may account to up to half the total number of ions that you're trying to analyze. If you could move those or out of the way of each other in maybe successive runs, that could open up quite a lot. I think that in Yates's analysis, the reason that he was able to see quite a few lower abundant things was because they weren't being interfered with by larger abundant compounds. Could we get methods of fractionation with sharper boundaries, like mass, for instance, or maybe homogenizing fractions from the chromatograph? Multiple runs with interleaving fraction selection. These are all things that you may be doing already. Using mass selection following chromatography. Now we're getting into chromatography MSM, as Rick pointed out the advantages already. So here's my proposal to you and my request. Alex and I would love for you to, I can send you a copy of this analysis spreadsheet. It's just as easy to use as I pointed out. It's automated. I did it, with Recorder. Then you share with us those results that you're getting. Now, here's the thing. There's no proprietary information that needs to be shared in this at all. Just the sample type and the list of responses and the method that you use. That's all we need to know. And then we'll compile these results. And if y'all can get us enough of them, we'll submit the results in this paper that we've been invited to produce. And y'all will be co-authors. Okay, so I hope you can get interested in that. So to conclude, thank you, ABRF, for recognizing the importance of these developments. It's amazing what's happened over the last 45 years to low energy fragmentation, how efficient, and its combination now with really high resolution mass analyzers has just been fantastic. I want to thank the organizer of this meeting. It's been very easy to work with you all. It's been a great pleasure. And to echo Rick's point, we're sorry that we're not there. But I'd like to point out I'm off into something else as well. And that is the philosophy of what science we're sure of, what we know. I'm on a campaign to try to counteract science denial. And the whole concept of science denial is completely oxymoronic with the fact that we rely on science in every way, every day. The success of technology and the concept that we don't know anything for sure is totally incompatible. And I've philosophically developed how that is resolved. And I invite you to this website, Chris Enke at substack.substack.com, and join the discussion of that topic. So thank you very much.
So I have a comment and a question. Hi, Chris and Rick. Great to see you. First, comment, thank you for this foundational technology. And then a question came in from a virtual attendee. Could I ask you both your opinions on strategies for relatively accurate quantitation of hundreds of targets, e.g. broad metabolite screening, when it's not practical to optimize transitions and include an internal standard for each individual target?
Let's assume for a moment we're talking about LC mass spec, as opposed to GCMS. I think that we oftentimes face this, right? We don't have internal standards for everything, but we like to get quantitative data. I think that to me the challenge that we face is that liquid chromatography doesn't give us the kind of separation power we take for granted in GC, and the ionization techniques we use in LC mass spec, primarily electrospray, doesn't give us what I call either universal or democratic response. That is, that not every compound you see with electrospray, and not everybody gets one vote. So ion suppression is a significant issue. So I think that's a challenge to do what you want to do, is to do quantitation on a large number of compounds without standards for them. Not that we don't all face that challenge of trying to achieve that, but I think those are the challenges, and I don't know that we have a good solution at this point. So that's the practical side. Chris, I don't know whether you have a philosophical side, but I assume we're talking about quantitation instead of identification on targeted work.
Well, exactly. And can you hear me? Yes. So the problem, of course, is response factor, as we were just pointing out. Response is not concentration because of the response factor involved. There is a technique in electrospray ionization that is not being developed to the degree that I really think that it ought to be, and that is exhaustive ionization. If you could provide, and the reason that we don't get, the reason that we have selectivity in electrospray ionization is because some halides are better at grabbing the charge than others, and pretty soon the excess charge is gone and we don't see what's left. And so exhaustive ionization has the opportunity, the possibility of essentially ionizing all the compounds that are present. And once you've made them into ions, then the response factor is just due to maybe some mass preferences within the mass spectrometer itself, which are easily characterized. So I think that that is a technique that really, I don't understand why it hasn't been more developed than it has. Just a few people, mostly Japanese, have been working on this, and I think that we're missing something major there.
Thank you. Are there questions from the audience? Please come up to the microphone.
Yes, maybe I can start. So I really liked both of your presentations, and you in the analysis of the signal response over analyte concentration, you treated everything as concentrations, as continuous variables. Of course, in some people are using mass spectrometry now to analyze single cells and very small numbers of molecules in the sample. At what point would you need to consider the discrete number of molecules? I'm thinking modeling how they work with the detector and the fact that you perhaps need more than one molecule in the trap at the same time to see something over the electronic noise. Yeah, so basically, can you still use your continuous models for single cells and discrete numbers of molecules? That was the question.
Oh, I could jump in here for a second. One of of the things that I've been working on and hasn't developed into a commercial instrument yet is distance of flight mass spectrometry. In distance of flight mass spectrometry, you have a charge detector at each mass position. The advantage of this is that that you get charge accumulation in the detector with multiple extractions, really in as many as you like. And so the dynamic range is automatically increased greatly. The chromatography requires us to dilute the sample in order to make it compatible with almost single line detection. With cumulative charge detection for each mass, you don't need to do that. And so I think that there is room for advancement in that direction.
I would concur. I think, you've obviously identified a challenging problem trying to do single cells where you have added stochastic issues that you wouldn't have when you're looking at a larger tissue, right?
Well, I have a comment or question for you related to that, is what happens then when we no longer can rely on our expected distribution of stable isotopes? Because the number of elements, atoms, are not large enough to give us what we expect to see.
Do we really get sensitive enough that we hit that limit? Or, when you think of Avogadro's number, we still have such a large number that we won't hit. It's an interesting question. I don't know whether anybody's looked at that. Chris, a new model for you to look at. How small of a sample before you have not enough, atoms to get a regular distribution, expected distribution of isotopes?
Maybe I'm wrong, but Avogadro's number is so huge that I think we're still several orders of magnitude away from worrying about that. But maybe I'm wrong. I'd love to know.
An interesting question. Well posed there, Sue.
I actually remember a discussion we had, Chris, many, many years ago that covered that.
Yeah. Good point.
Are there any more questions? Well, if not, we'd like to thank you and congratulate you again on this really wonderfully well-deserved award. And thank you so much for fabulous presentations.
Well, thank you too so much. Bye.